Good evening and welcome to my YouTube channel, which is called Pearson and Excel International A-Level Mathematics by Mr. Kamotho. And we shall be discussing in this video Pure Mathematics Book 3, and we are still continuing with Chapter 5. And we will be introducing ourselves to what we are going to call Euler's number, or E. We are going straight to page 105, and with this one you talking about this is exponential, and logarithms, P3 topic 5. And I want to introduce something on page 105 that talks about y is equals to e raised to power ax plus b plus c. And if you read the statement under 5.2, we are told that exponential functions of the form fx is equals to a raised to power x. Exponential functions of the form fx equals to a raised to power x have a special mathematical property. They have a very special mathematical property, and it is observed that the graphs of their gradient functions are a similar shape to the graphs of the functions themselves. What does that mean? The graph of the gradient functions, they have a similar shape to the graphs of the functions themselves. And I want to just bring something to do with y is equals to 2 raised to power x. And later on, we will understand that the dy dx of this function is given by 0.693, of course, with more numbers, but we multiply that by the function itself, 0.693 ... times 2 raised to power x. What this means is that you will see that if we take the graph of y is equals to 2 raised to power x, and you get the graph of the derivative, or the dy dx of the same is going to give you 0.69 times 2 raised to power x, meaning it will always be less than the original, because it's the same function multiplied by 0.69, so it will be less than this. So this is going to give you something that goes like that. It is important to note that as much as we are going to have 1 there, this particular point is going to be this constant, because 2 raised to power 0 is still 1 times this, it becomes this constant, 0.69. So that shows it will always be less. It will always be less than than the graph of y is equals to 2 raised to power x. Now, I want us to just compare this closely versus, let's talk about y is equals to 3x, and the dy dx of this is going to be 1.09 times 3 raised to power x. You will notice that when we have this function y is equals to 3 raised to power x, the derivative of the same is 1.09 multiplied by the function itself. So 1 point something means if you plot the graph of the same and you have the graph of y is equals to 3 raised to power x, then times 1.09, you'll realize that the graph of the derivative will now be greater than the graph of the function. Yes, this is dy dx, which is 0.69 times 2 raised to power x, and you will see this is now the graph of dy dx, which is 1.09 times 3 raised to power x. Let us notice something there. It is very important for everybody to note that in each case, the derivative function of x is equals to k multiplied by the original function, where k is a constant and a k is a constant. As you can already see here, the graph of the derivative was smaller than the graph of the function. Here, the graph of the derivative is showing the values of y which are greater than the graph of the original function. So it is important to note that when y was 2 raised to power x versus y is equals to 3 raised to power x, there is a function in between these two. Whereby the graph of the derivative will be exactly equal to the graph of the function. Because if it was smaller there and it was now larger here, then there was a time when they were exactly at the same point. So as a increases, k also increases. You will see that, because you will see here when y was 2 raised to power x, dy dx was 0.69 times 2 raised to power x. Here was 0.69. When y was 3 raised to power x, the dy dx was 1.09 times 3 raised to power x. So here k was 1.09. So it is important to say, as a increases, or as a, let's talk about increases, so does k. So does k also increase. So you will notice that something unique happens between when a is equals to 2 and when a is equals to 3. That's where I'm talking about the derivative somewhere between 2 and 3. 2 and 3. The derivative will exactly show the same graph as the original function. There is going to be a value of a where the gradient function is exactly the same as the original function. And this occurs between, let's talk about between, when a is equals to 2 and a is equals to 3. The gradient function will be somewhere between a is equals to 2 and a is equals to 3. The gradient function will be exactly equal to the original function. What does this mean? This occurs when a is approximately when a is approximately equal to 2.71828. And when a is approximately equals to 2.71828, the graph of the derivative will be exactly the same as the graph of the original function. And this is now what we call the Euler's number. The exact value is represented by the letter E. This is now what we call the letter E, and it is a constant just like pi, or how we use pi mathematically. That is how we are supposed, or we are going to use E in calculations. It is a very important mathematical constant, and it is called the Euler's number, and we are going to use it very, very effectively and very abundantly starting now. So at this particular point, it is a constant, it is an irrational number. So it is now at this point that we say for all real values, of x, if fx is equals to e raised to power x, then dy dx is equals to e raised to power x. Now that we are talking about the Euler's number, we said that when a is 2.7182, then the dy dx will be the same as the original function. So this is the same as saying if y is equals to ex, then dy dx is equals to ex. And it follows that a similar result holds for the function such as e raised to power, let's say 5e. And for all real numbers, we can also say, extend this and also say, also if fx is equals to e raised to power kx, then f prime x is equals to f prime x is equals to k e raised to power kx. Remember, if we fx, of course, we're talking about which is the derivative of x. We can also call it dy dx either way. And at the end of the day, if we can decide to write it in terms of y, if y is equals to e kx, then dy dx is equals to k e kx, k e raised to power kx. Now we will talk about this extensively in the following videos, but for now it is important to note that we have I've explained the Euler's number, whereby if we are talking about exponential functions, a raised to power x, when a itself is 2.71828 or thereabout, then its derivative is exactly equals to the original function, and that is what we call the Euler's number. So please subscribe in my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho. Share widely, and of course like. All right.